So my presentation title is Leveraging Big Earth Observation Data for Geohazard Modeling and Infrastructure Resilience. So my name is Weiwei Zhan. I joined UCF in 2023, August, as a assistant professor in geotechnical engineering. At UCF, I direct the GEI lab, Geosystem Engineering and Intelligence. Prior to that, I received my bachelor's degree in engineering geology from China and a PhD degree in civil engineering from Clemson University. I did 2 postdoc training, one at Tufts University and another one at the University of Texas at Austin. My research interests include geohazard assessment and mitigation, geotechnical earthquake engineering, remote sensing and GIS, AI for earthquake for nature hazard engineering, uncertainty qualification, and geomechanics. At UCF, I teach geotechnical engineering, soil dynamics, and foundation engineering. I also taught risk engineering at Clemson. So I'm strongly motivated to use multidisciplinary solutions for mitigating the costly, diverse, and complex nature hazards. So specifically, I focus on the geohazard modeling and mitigation. I study 3 types of geohazards, including landslide, liquefaction, and earthquakes. So I use multidisciplinary and multimodal surveys and data, including the geology survey, geotechnical testing, and remote sensing and seismic monitoring. Using this data, I develop a data-driven model and physics-based models to reveal the patterns and the mechanism of different hazards. And for the hazard mitigation, I emphasize on the near real-time models so that I can mitigate the nature hazard. I also emphasize on the trade-off between the model accuracy and the interpretability. So I also did the contributions about how to investigate the spatial temporal variability and of different nature hazard, and also add the uncertainty qualifications into the models. Today, I will highlight the applications, the usage of 2 types of Earth observation big data. The first one is images collected from different remote sensing instruments. And the second one is waveform data from a lot of seismic stations. So first, I will talk about the landslide study. I have studied a lot about using different type of remote sensing techniques to regionally, basically to detect and monitor the landslide stability. For example, we want to provide some earthquake landslide early warning criteria, so to set the alarm about the landslide hazard. This work, we still have some challenges. Basically, it's this type of success of this work is also influenced by the complexity of our slopes. So we need some better techniques to penetrate the slope. Recently, I also leveraged the big data and the computer vision techniques in this regional landslide mapping task. So specifically, we build a large landslide inventory and use deep learning to map the landslide boundary. And we also find the data fusing, the model fusing can mitigate the over predictions issues of the deep learning. And landslide can occur on its own, but most landslides actually are triggered by some other strong nature events, such as earthquake and typhoon. So earthquake and typhoon can trigger thousands of landslides in a very short time window. And so it's very important to investigate the spatial distribution pattern so we can predict the hazard for future events. So I use the satellite survey and also the UAV and the geology survey basically to build the digital landslide inventory. And then we can run the geospatial analysis to investigate the spatial distribution pattern. For example, the hotspot of landslide in a normalized slope. And using this data, we can also develop predictive models and map for predicting future events. I also explore how to use statistical learning and physics-based modeling to predict the post-value travel distance of large rock avalanche. So it's very important for the risk analysis for the landslide. So for this purpose, we build a specific landslide mobility database, and we develop the statistical model for predicting the maximum travel distance. And by comparing the data from different inventory, we can identify some controlling factors. For example, the rock avalanche shows a much stronger mobilities than other type of landslides. To understand the reason, we also employ the physics-based modeling. We found that the rock fragmentation process actually release additional energy that contributed to the actual mobility of this type of landslides. The second nature hazard I study a lot is about the soil liquefaction. It can cause significant loss to urban cities within the seismic zone. For example, it cost $15 billion to the 2011 Christchurch earthquakes. And it's very difficult to predict where and how severe will the liquefaction hazard be, because it can range from a small scale sand buoy to a building scale differential settlement, and to a community scale flow type landslide. For example, this one killed more than 4,000 people in a short time. So the conventional method rely on the intrusive geotechnical data and a limited number of case history to develop the model. So I developed two types of near real-time soil liquefaction hazard assessment method. So the first method uses a waveform. We call it the waveform-based liquefaction quick detection. So basically, we use statistical learning and signal processing to assess the liquefaction hazard immediately after the earthquake. So the hypothesis is driven by our understanding of the soil mechanics. We know the soil liquefaction can change the soil properties. That will affect the seismic wave propagation. So we can expect some difference in the earthquake waveform. So we build a database basically to use a waveform to detect the liquefaction. So this here is the methodology. We use a different signal processing technique to extract the useful features and develop the compile database and develop a classification model and validate our model. So there are some potential applications of this waveform-based method. It can be used in real-time hazard mitigation for the widespread pipeline system. For example, if the sensor can detect the hazard, we can shut down the gas supply in the pipeline, so that we avoid some gas explosion hazard. The second approach for liquefaction is called the geospatial liquefaction hazard modeling. Basically, it takes advantage, it learns the distribution pattern from the historical liquefaction observations and use some statistical or machine learning model to predict the hazard for the future events. So I developed new geospatial models, including the development of new database and the add the machine learning and the feature engineering techniques to improve the model accuracy. I also add uncertain quantification capability to this type of model. Basically, we can tell the confidence level of every predictions. So the third main area I'm exploring right now is about the waveform-based engineering applications. So we have a lot of seismic network. They are continuously recording the earthquakes and also environment noise. There is a rapid growth of this waveform data. So this big data actually lead to very successful applications in the science side. For example, in the seismology, we can better quantify our earth structures. So I'm particularly interested in the engineering application of this big waveform data. So recently we have explored how to use this big waveform data to improve our accuracy of ground motion modeling. Basically, we want to predict the ground motion intensities for any future events. So we integrated the AI and the new data into this modeling, and we have successfully applied got 2 USGS funding. And using this bigger waveform data, we can also improve our understanding about the wave propagation theory. So right now we are using a very old method, so it does not do a very good job for predicting the wave propagation. And I'm also interested in how to use this data to develop real-time disaster and environmental monitoring. So I'm particularly interested in how we can use this waveform data to detect the nature hazard and also both and the human hazard, like the explosions and the traffic crash. So this slide shows my future research plan. In the last 6 months, I have adapted myself to solve the local problems. I have developed a proposal for the remote sensing enhanced sinkhole early warning and risk management. This proposal is pending with the FDOT right now. I have also worked on the coastal erosion modeling and mitigation. We are ready to submit this proposal to NSF. And the third area is my main field. So it's AI for earthquake engineering and science. So we have a pending project with the USGS. And I also got interested in the digital twin and the geohazard research and education. For the long-term plan, I'm interested to bridge my multi-hazard geohazard assessment knowledge to contribute to the infrastructure resilience and the community resilience. So I'm interested in the multi-hazard infrastructure resilient design and hazard infrastructure human interaction. I also hope to make some fundamental contribution to the soil mechanics under extremes. I always welcome collaborations. particularly I'm interested in working with people in the digital twin, deep learning, smart sensing technique, and also in other domains like the smart city and energy systems. So right now we have our lab have 2 members. We are about to grow in the coming semesters. I have really enjoyed my time at UCF so far. I think the biggest reason we have a very fantastic faculty team. In the past several months, I have talked with, I found some common ground with many faculties in our unit and outside our unit. So I hope we can make some work together in the coming years. And I also have a lot of external collaborators. So some of them are listed here. My previous projects are mainly funded by the USGS, AIG, NSF, NASA, and the DOE. Again, I always welcome collaborations. If you have got any interest, please contact me using this email. Thank you.